Alright, so these were the things that we studied up to last class. Now we're going to move on into a few equations. Right, so first equation that we're going to do, or first graph, sorry, that we're going to do, is a graph of displacement versus acceleration. Can you tell me what this graph is going to look like, Maksud?
Linear but opposite to a straight line.
So negative. Why? Because a is equal to minus omega square x. So if that's the case, then you're going to get a straight line which passes through the origin like this, right?
Yep.
Beautiful. So what's the gradient of this graph?
Oh, no
Come on.
idea. No idea.
It's going to be minus omega square.
Oh, it's okay.
Like, come on, man. Dude. All right. Yeah, you're not so smart sometimes, aren't you? Okay, moving on. So this was that. After that, we need to talk about the energy conversions. So imagine again a pendulum, all right? So someone saying W. I want to hurt people. So say we take a pendulum and it moves between these 2 points, and there's this book diagram that everyone's seen. Here the GPE is maximum, right? The KE is 0. Here the GPE is maximum, KE is 0. Why is the KE 0, Maksud?
Because it's stationary.
Yes. Here the GPE is not 0, it's minimum. The KE is maximum. So basically we need to use this to plot a graph or sketch a graph of how energy changes occur with oscillations. So, oh yeah, you could keep a copy and paper at hand, then you could jot down the important points. It would make life easier for you. Some of my O-level students do that, and it's nice to see them when they bring them back and show it to us. So say this is an oscillation of a system, right? So as it oscillates, these are maximum displacement points, right? So at maximum displacement, the energy is going to be all potential. And at zero displacement, all the energy is going to be kinetic. So if we want to convert this into a graph, what would the graph look like? Number one, the axis of the graph is going to be scalar. Maksud, why am I drawing a scalar graph? Can you tell me?
Energy is
scalar. Excellent, yes. Yusa, thank you for joining us. Students are complaining that the videos aren't titled properly, so they can't go back and watch them. So could you please go and label the videos properly, because and also what the content is, because students want to watch what each one means. So yes, please do that. All right, moving forward. So I'm going to use again 2 colors. So blue is going to represent kinetic energy. So here the kinetic energy is maximum, right? So what's going to happen? The graph is going to be like this. It's going to be a maximum here. It's going to be a maximum here, maximum here. Basically every time it reaches zero displacement. And it's going to be 0 here at these points. Ooh, that's basically here and there. So the graph is going to be something like this.
Is this potential or is it kinetic?
This is going to be kinetic. Why is it kinetic? Because it relates to the initial point, which is at 0, right? The velocity is maximum. And the potential is maximum at these points, right? As this shows. Maximum, 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 maximum. So basically this means the potential graph is going to look like this. Ugh, it was almost perfect except for the last one. The pain. The pain.
Can you write GP in red? Can you write GP in red?
Oh yes. GP. And then I'm going to use orange to show total energy. Total energy. Right? This is what the graph looks like. So this is this versus time. Right, that's one graph. This is assuming no energy is lost from the oscillation, which is basically an undamped oscillation. All right, then what if we try to draw the same graph? All right, let's try to draw it here. What if we try to draw the same graph, but instead of energy versus time, what if we draw energy versus displacement. What will that graph look like? So, oh man, I keep smudging. So energy versus displacement, so minus x plus x. So what will this graph look like? Again, if we use the red and the blue to represent GP and K, the GP is going to be 0 at this point, right? So this graph is going to go like this and like this. And the KE is going to look like this and this. And the total energy is going to look like almost the wrong pen. Yes, it's going to be constant. All right, yes, half circle. That's right, Susanna Jacinta, right? If that's how you pronounce your name. Not exactly a half circle. It's more of a parabola. So, but yes, it's a graph. So the reason I drew these together is because so you understand this looks sinusoidal. This does not look sinusoidal. That's an important thing. All right, moving on. So these are the energy conversions that we see in projectile motion. Oscillations. Now we need to talk about, what do we need to talk about? Damping, right? Oh, yes. This is a Newton's cradle. And we're going to use this to explain stuff. So what I'm going to do is I'm going to hang a few of these balls off the sides. Maksud.
Sorry, professional.
Yes, stay professional. Yes, like, you know. So yes, so there's only one ball now. So if I disturb it once, this is a free oscillation. It's moving at whatever frequency it wants to move. And the frequency now is its natural frequency. When it's oscillating, it has a natural frequency. As the pendulum is moving, over time what you're going to see is that eventually it stops. What?
Can we define
One of them said I hung up my balls. Oh my God. I'm going to ignore these comments. I shouldn't read them. So this is not going to stop. Why? Because, well, eventually it will, but it's not stopping now because the oscillation can be considered to be undamped. In reality, it's not undamped. There is some damping. So it's undamped because that basically means no energy is lost from the oscillation. And in theory, if this was undamped absolutely, then it would constantly oscillate forever. But because there's some sort of damping, slowly the amplitude of the oscillation will decrease. As I've been talking, you might see that the amplitude has slightly decreased. Has it, Maksud?
Almost. It's unnoticeable.
Anyway, so that's basically one of the things that we have to find out. Yes, Yusa, I told you all the things I told you. Go and do what I told you to do. So now what happens is this oscillation, it's slowly losing energy, which shows it's a slightly damped oscillation. If it was undamped, it would go on forever, as I just said. And now, because I'm not disturbing it, the frequency at it which is oscillating is called its natural frequency. So it's really easy, really simple stuff, really straightforward. Now, if I was to take the pendulum, everyone's done this, so they know this. You first disturb it, you find out its natural frequency, and then what you do is you start oscillating it at its natural frequency, or a multiple or a factor of its natural frequency. Are you seeing that, Maksud? Oh, missed it. There you go. So if I was doing this perfectly, then what's going to happen is, can I do it? Do you think I can do it?
Excuse.
Oh!
You could do it like a Rasta, then you could do it like a logo.
Oh, no, man. Too much. So yes, basically this is me doing resonance. When you're forcing a system to oscillate at its natural frequency, when a system is forced to oscillate at its natural frequency, it causes large amplitude oscillations. And that's basically what you get here. So yes, this is the concept of oscillation. So let's write down the stuff that I just talked about. Right, number one, this is a free oscillation. So if it's a free oscillation, what does this mean? This means it's occurring at natural frequency. Right, so this is a natural frequency. So, and number two, it's a damped oscillation. Why is it a damped oscillation? Because amplitude is decreasing, and yes, it's because of
Air resistance.
air resistance. Right? So let's just take a minute and try to draw this oscillation with time. So if I put this oscillation here, can you guys see the oscillation? Yes, you just barely can. So with time, if I was to draw the oscillation that we're seeing, we start from maximum displacement, and then what happens? It slowly decreases. Time period roughly stays the same. So as you can see, the loss of energy during this oscillation is exponential. It should be like this. So basically this line ideally should start somewhere up here. So this is a damped oscillation, and the damping is underdamping. Why is it underdamping? Because the system started with large oscillations, and then multiple oscillations later, slowly it's decreasing. So this is underdamped, and these are the properties of this oscillation. It's a free oscillation occurring at natural frequency. Come on, focus here. Oh man, it doesn't focus. And damped oscillation because the amplitude is decreasing, and that's because of the air resistance, right? So the blue line is what we call underdamping. So the other situation is, coming back to this, if this was underwater and we were to take it like this and then release it, then most likely what you would see is after you release it, it slowly moves in the water and eventually stops here, right? So that is basically it stopping as fast as possible. So that's basically this thing called critical damping. So critical damping by definition is this system or method or situation where you cause the system to slow down the fastest rate possible. And this is basically critical damping.
So it won't oscillate at all.
Correct. It will not oscillate. So the red line, by definition, is the shortest time required to stop. So yes, critical damping. And then, if we were to repeat this experiment again, but this time not in water, if we repeated it in engine oil or something really thick, what's going to happen is, or even thicker, what's going to happen is you release it, it's going to move really slowly. It's like critical damping, but it takes more time. It's like critical damping with extra steps. So what that is going to lead to is a graph like critical damping, but it's going to take even longer. So it's going to start from here, it's going to go like this slowly, it eventually stops here. That's a nice curve. So that's going to be overdamping. Overdamping, or it's also called heavy damping. And underdamping can also be called, come on, Maqsad?
No idea actually.
Light damping. Dude.
Very in the dark with this chapter.
Well, you should be in the light now. So yes. We have underdamping or light damping, we have overdamping, heavy damping, and the perfect sort of damping is critical damping. We usually want to do critical damping. That's when we want systems to lose energy as fast as possible. For example, buildings, sometimes car suspensions, and these sort of things. All right, the next thing that I showed was the concept of resonance. So we found out its natural frequency, correct? And then we started forcing it. This is a forced oscillation, all right? We're causing forced oscillations at its natural frequency. Yes, we're coming back to that. So we're forcing it to oscillate at a certain frequency. And the frequency at which we're causing it to oscillate is basically its natural frequency. So if I was to just disturb it once and let it oscillate, this is a free oscillation. If I am constantly disturbing it, then this is a forced oscillation. So resonance occurs when you cause forced oscillations at the natural frequency, right? So that's basically resonance. So resonance can be defined as, I'm not going to write the whole thing. Resonance can be defined as when a system is forced to oscillate at its natural frequency, causing large amplitude oscillations, right? I'm going to cause large amplitude oscillations, big amplitude oscillations. So yes, that's basically what large amplitude oscillations mean. So the thing is that damping and resonance do have a relationship. If the system is not damped, okay, we're going to draw a graph of how the amplitude varies with the natural frequency or the forced frequency. So this line, I'm going to draw a line here. This line represents the natural frequency of the system. So say I force the oscillations starting at a low frequency and I gradually increase this frequency. So as the frequency increases, you're going to see there's a sharp increase in the amplitude. Why does this happen? That's because resonance is occurring. And then the moment you cross, this is basically, you can say Fn, natural frequency. The moment you cross the natural frequency again, the graph will rapidly decline away. So why does it decline away again? Because you're moving away from the natural frequency. So this happens at multiples of the natural frequency, or factors basically. Basically that means I can make this resonate also if I even disturb it every few oscillations. So this is also resonance. So that basically means you don't just have to do F, but multiples of F will also work. So this is what we see here. Now, if the system was damped, again, if this was underwater, blah, 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 and all of that, if we were to repeat that using this, what would you see, Maqsood?
What?
All right, forget that. So yes, if we cause damping, then the amplitude increase won't be so aggressive. It's going to be slightly less. So if that happens, what do you see? The graph won't be so sharp. It's going to be a little damp like this. And if you cause more damping, it's going to be less. Even more damping, it's going to be even less. So basically really sharp and then decreases and becomes really blunt. So that's basically something that we call the frequency response curve. Sometimes if you want to have the real accurate stuff, the natural frequency slightly decreases as you continue down like that. And in questions they sometimes say that, like, you know, the experiment is repeated with feathers on it, or the lump of clay, you started an experiment with a lump of clay and then the lump of clay turned into, like, you know, it was flattened into a disc, and, like, you know, these sort of things. So under such situations, basically, they're basically increasing the air resistance acting on the system. Ultimate target being that the oscillation has more and more damping. And the more damping you have, the resonance will be at a lower value. So this is basically the concept of frequency response. So that's pretty much it. Yeah, Ismail Jubair, that's what I basically did. I did shift the frequency down a little bit. The time period increases. That's one of the small side effects of damping. So that's basically it. That's the concept of simple harmonic motion. I think we've done the entire chapter, have we? Maqsood?
I think so.
Did we miss out anything? Damped oscillation and resonance occurs at forced oscillations at natural frequency, resulting in large amplitude oscillations. So yeah.
We only have 3 degrees of damping.
Oh well, it's a continuous spectrum. It's not like it just happens at one specific value and then never happens again. But for your O levels, for your A levels, A2s, yes, you can say that this is all that you need to know.